We're continuing our notes here on day 2. Last video we did this front page only. We were looking at the trig identities, and we were using our Pythagorean theorem to find the missing side of a triangle to establish various trig ratios. We were using those trig identities down here, and that's about where we left off. So we're continuing on the next page, and this is shifting gears a little bit because we're not focusing quite so much on the trig identities. Instead, what we're doing is taking it back to things like the unit circle or some application problems, a few story problems down there, and that's what we'll be looking at today. So here's example 10. Find the value of this theta in degrees and radians. Notice they are limiting us to quadrant 1, and that's true for both of these, right? So in other words, we're not going to have a bunch of answers for a bunch of quadrants, just one answer for both radians and degrees. They're challenging us to do it without a calculator, and that means it's probably going to be tied back to the unit circle. But we don't see this value on the unit circle anywhere, root 3 over 3. So we have to try to figure out where are we at on the unit circle where, when you take the cotangent of that point, you end up with this result. So there's a couple ways we can approach this. I'm going to show you just the guess and check approach. And what we're doing is we're saying, well, this root 3 is a key piece. Where would you encounter that in quadrant 1 on the unit circle? So just remembering what that first quadrant looks like. We have a few key points here, right? So this point is located at root 3 over 2 comma 1/2. This point is root 2 over 2 comma root 2 over 2. And then this point is the 1/2 comma root 3 over 2. And we're saying, hey, we see this root 3 showing up in these locations, but of course it's represented by a root 3 over 2. Our problem is a root 3 over 3. So something must be happening that turns this coordinate point from the unit circle into this particular value that they're giving us. So we have to go back and remember that cotangent is the ratio of cosine over sine. All right, so that is a trig identity there, but we're taking it one step farther because on the unit circle, we know cosine is associated with the x-coordinate and sine with the y-coordinate. So the question is, which coordinate point do we use such that when we take the x-coordinate divided by the y-coordinate, we end up with this result of root 3 over 3. Like I said, this is the guess and check approach, so let's guess 30 degrees. Okay, so if I were to take cotangent of 30 degrees, what we need to do is we need to take the x over the y-coordinate, and at 30 degrees, the x-coordinate is that root 3 over 2. The y-coordinate is 1/2. Notice both fractions have the same denominator, so they will cancel out. And this simplifies to root 3. Okay, that is not what we're looking for, so we guessed wrong. So it's probably the other one, but let's work it out. What would be cotangent at 60 degrees? Again, it's the x-coordinate over the y-coordinate. Here at 60 degrees, the x-coordinate is 1/2. The y-coordinate is the root 3 over 2. Again, they have that denominator of 2. That cancels out. We have 1 over root 3. Hey, that doesn't match either. But wait a minute. We're not done. We have to rationalize the denominator. There it is. So that means we're at 60 degrees. So we want to answer this question in both degrees and radians. So we would say this occurs at 60 degrees, which is pi over 3 radians. Okay, so notice what's happening here. This number looked very mysterious, and the reason why it looked mysterious is because we were having to rationalize the denominator. We had to rationalize the denominator because the radical was in the denominator, right? And the 2's canceled out. That's why we weren't seeing the value of 2 that would normally be found on an x and y coordinate. So when we were approaching this problem, we were looking at this root 3 over 3. We knew that value wasn't on the unit circle. So the takeaway here is something must be happening with both x and y coordinates that it's simplified and changed to ending up with this, right? So we're kind of working it backwards. We're trying to figure out what would happen with the x and y coordinate in this way would it actually simplify to what we're looking for? And it does here. Right, so that's our triangle. So 10, we did that without a calculator. In example 11, we're now going to use the calculator. And just remember that you need to be in degree mode if you want an answer in degrees, and you have to be in radian mode when you want the answer in radians, so you're toggling back and forth. Recall here that when we have a trig function of an angle, what we're trying to do is get that angle by itself, right? We're trying to isolate the variable. And to do that, we have to get rid of the cosine, but you can't just divide it away. You can't divide cosine because cosine is not a number. What you have to do is do its opposite, right? We call that the inverse. So you take the inverse cosine of both sides, like this. So don't call it cosine to the -1. It's not an exponent. It's just a notation for the inverse. It's the opposite of that cosine. And that's what they're printing here next to the boxes, right? So the cosine and its inverse cancel out. That's how you isolate the angle of rotation. And then from here, it's just calculator work. So you have to be in degree mode to get a degree answer. And then you have to switch over to radian mode and type this in all over again. And there you are. So now for a few applications. In this section, we're going to look at two different kinds of triangles, and I'm going to add an example here. So here you see example 12. Let's call this 12 part B, okay? In example 12, it's a fairly regular looking triangle. I mean, it's a normal looking triangle. We've got a right angle, we have an acute angle, we have a hypotenuse that we're trying to find. All right, so in a case like this, we're bringing it back to our trig functions. These are the ratio of two sides. So that means you always have to identify that acute angle. That's your reference angle. So then you label the sides. So this is the adjacent leg touching that reference angle. This is the opposite leg of 20, not touching the reference angle. Of course, the hypotenuse is opposite the right angle itself. So we have to find r, so we're going to use the hypotenuse, and we have a value on the opposite leg. So we're using these two, the opposite and the hypotenuse. So sine is what we want. Sine of the reference angle, 42 degrees. So again, our calculator must be back in degree mode. Equals opposite over hypotenuse. Now your variable is in the denominator, which means you set up a proportion so that you can cross multiply. So we have r times the sine of 42 degrees equals 1 times the 20. And then to get r by itself, divide away the sine of 42. All right, so that's what we'll type into our calculator. Sine 20 divided by sine of 42 degrees. We get 29.89. No units here, so that would just be our length. Now, what we had is an angle of elevation. This is our horizontal reference line, and you can see that we are rotating upwards from that horizontal. Okay, so an angle of elevation always has to have a horizontal reference line, and you rotate upwards. Right? That kind of makes sense. The angle of depression now, you also need a horizontal reference line, and this time you rotate downwards so that you are underneath that horizontal reference line. So take a look at the example 12 we just did. Here's our triangle. Do you see this angle up here? This is not the angle of depression because we do not have a horizontal reference line. So if we were to identify where is that horizontal reference line, it would have to be a horizontal line right here, passing through that vertex. There's your horizontal line. And what that means is your angle of depression is here. It is outside of the triangle. So the way this triangle is drawn, we see that the angle of depression is outside the triangle. The angle of elevation is on the inside. Now, something that you've learned a long time ago, back in geometry, is that if you have parallel lines, so these are your parallel lines, crossed by a transversal, here's the line crossing over those parallel lines, you have a very special angle pair. These are alternate interior angles. They're on alternate sides of the transversal, and they're interior. They're in between those two parallel lines. Right? So these are your parallel lines. And that means these are going to be congruent. So this 42-degree angle that you see here is also found here. That's also 42 degrees. So what we're saying is that if a problem gives you an angle of depression, you can actually just put it here, and it becomes the angle of elevation. And that's what you want. You want an angle on the inside of the triangle, not on the outside. All right, here's example 12, part B. Here's my right triangle, and we have a 30-degree angle right here. Let's give ourselves a hypotenuse of 18, and this base will be the mystery. All right. Now you might say, okay, I got this, SOHCAHTOA, right? No, if we have a special right triangle, we're not going to use SOHCAHTOA because that would give us a decimal approximation. We want exact answers if possible. So remember that with your special right triangles, like your 30, 60, 90, we have these formulas, right? Hypotenuse equals 2 times the short leg, and long leg equals the short leg times root 3. All right, so now we're labeling the sides of the triangle not as the adjacent or the opposite, but instead as the short leg, long leg. So here's your short leg, here's your long leg, and of course the hypotenuse is across from the right angle. So my hypotenuse is 18. That equals 2 times the short leg. Therefore, the short leg is 9. So now we know the short leg is a length of 9. And then we'll take that result and go to the next equation. So the long leg, which we're calling x, will be 9 times root 3. There it is. So no decimal values when you have a special right triangle. So we've seen this before. We had done this a few pages back. These are the two for your 30, 60, 90. And remember, you also have a 45, 45, 90. And so in a case like that, all right, if you have a 45, 45, 90, you have hypotenuse equals leg times root 2. So that's the other case. We'll finish up with example 13 now. All right, so example 13, it's an application problem, a story problem, right? So this is like a cable car that goes up the side of a mountain. If you think about that, it's not really run on cables, but it's on track, right? So this track on the declined incline in Pittsburgh is about 800 feet long. So we're going to represent the side of the mountain with that slant. So we have to turn this into a right triangle. So let's create the vertical side from one endpoint, the horizontal side from the other endpoint, and there's our right triangle. So here's our 800 feet. Right, so here's your little trolley car that's going up the side of the mountain, and you end up here with a nice view of the city. So it tells us we have an angle of elevation of 30 degrees. All right, so there's our angle of elevation. So because that's a special right triangle, we're going to use our formula. So that means we have a short leg, a long leg, and here's our hypotenuse. So it says this track is about 800 feet long, and the angle of elevation is 30 degrees. They're also giving us something else. The average speed of the cable cars is about 320 feet per minute. So if you were traveling 320 feet per minute, that information also goes here on the hypotenuse because that's where the path takes you, right? So that's the speed, and that's the distance. So this question is asking how high does the incline rise? So how high means we need to find the height of the mountain. All right, so that's the short leg. So that's fairly straightforward. Hypotenuse equals 2 times the short leg. Right, so 400 feet is what we have. Let's just add one more part to this. Let's add another question. So again, call this part B. Now the question is, how fast? How fast is the vertical rise? How fast is the vertical rise? Now we already know how fast the car is traveling, but this is not the vertical rise. This is the rate at which we're going up the slope of the mountain. The question is, if you start here at 0 seconds, 0 minutes, and after traveling 800 feet, 320 feet per minute, you end up here. The question is, what is your change in elevation, 400 feet, and what is then the speed at which you are changing your elevation? Okay, so instead of using the 800 feet, which measures distance, we're now using the 320, which measures the rate. So it's still the same formula. Hypotenuse equals 2 times the short leg. Hypotenuse is now this time 320 feet per minute. So that means my short leg, the vertical side, is going to be 160, and that's feet per minute. Notice this is measuring speed. Distance over time is your speed or your rate. And we just happen to have distance in feet and time in minutes that was provided to us already.